something that I'll give you some tips on as we get started. All right, so at this point, we are seeing the events that take place with our neuromuscular junction. We're understanding we've got a sarcomere. The sarcomere has the actin and the myosin, okay? All these events working together are hopefully going to make it do this number for muscle contraction. So when the muscle contraction occurs and we see those events, when we have the nerve impulse travel down, release the acetylcholine begins to affect the ligands. We begin to pass that potential along the muscle fiber by way of the voltage gated. Do you guys remember the T-tubules? Okay, and they run transverse through that muscle fiber, that muscle cell, and basically from sarcomere to sarcomere to sarcomere to sarcomere, where you've got T-tubule, 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 this is going to release these ions at that point. That is in contact with my sarcoplasmic reticulum. What did we say again that was in, what ion is in my sarcoplasmic reticulum? My calcium. So, when we look at the structure, we get an action potential, and it begins to pass along the cell. That's the sarcolemma, that's the plasma membrane. That reaches the T-tubule, which have a terminal cistern, okay? That's cistern, that's means cistern, okay? Comes into contact with my sarcoplasmic reticulum, which is known as smooth endoplasmic reticulum. When we get this coming together and it affects that sarcoplasmic reticulum, this means calcium is released. So all of that activity, starting with that nerve, okay, all of that activity comes down to the point of that sarcoplasmic reticulum and the release of the calcium. At the point that we get the release of the calcium, that calcium then will come into contact. You guys remember the actin myosin, and then it had the troponin, tropomyosin, the little rope and the little pieces at the joint of rope, okay? Remember, that calcium attaches to the troponin on the tropomyosin. If that occurs, when that calcium attaches to that troponin on that tropomyosin, which is covering my active site, it's going to cause that rope to shift. If that rope shifts, what has now become available? What's now exposed on that actin? The active site. If the active site is exposed due to the structure of the myosin heads have the ability to attach. Now, when this takes place, okay, we create what's called a cross bridge. We have now joined together this actin and the myosin, and they've termed this a cross bridge. Does that make sense? Now remember, when this occurs, when we have the attachment of the myosin to the actin. The one thing that's needed for the myosin to release from the actin, we need energy. We need ATP. When we have that connection made between the thick and the thin filament and it pulls, in order for it to release and for that head to go back down, to possibly come up, connect to another active site, and pull again, that can only be done in the presence of ATP. So, one of the things about a muscle cell, especially the skeletal muscle and the cardiac muscle, mitochondria tend to be huge. They tend to be very plentiful in the skeletal and the cardiac muscle. What am I missing? Smooth. Okay? Smooth is, well, it's going to be its own thing. Okay? So, what I get is I get a process for this movement. And it starts all the way back at my nerve with the impulse. So, once I get the impulse, once I get the release of the acetylcholine, once I get the gates open, once I get the sodium going, and I get the sodium going, which affects the endoplasmic reticulum releases the calcium, I'm at that point right there. I am now at these protein filaments of my sarcomere, of pieces, from piece to piece to piece to piece. Now, here's what will happen. The calcium that gets released, it attaches to the troponin. When it attaches to the troponin, makes the tropomyosin shift. When the tropomyosin shifts, my active sites are now exposed. My active sites, because it took energy to make them release, this means they're ready to attach, because they're energized at release, not at attachment. Does everybody understand that? A lot of times what happens with ATP comes in, attaches to something, gives it the energy, and it works. In this case right here, that myosin head has the energy and it's ready to go. But it can't do anything until the calcium is released and the troponin and tropomyosin are activated. All right? So that means when the tropomyosin shifts and it attaches to the active site, to make it release, you got to energize it. So that the next time that the active site's available, it's already ready to attach. Okay? So it kind of seems backwards. Does everybody see that? Yes. And makes rigor mortis real interesting. Familiar with rigor mortis? Yeah, you sit up with the dead, so the dead sit up with you. Y'all ever heard that? But there's a comedian that sings a song about it, that he was sitting up with the dead, so the dead sat up with him. It's real funny. Okay. Anyway, alright, back to topic. Okay, so once we have the calcium attached to the troponin, tropomyosin shifts, active site exposed, myosin head attached. When the myosin head attaches, this is now termed my cross bridge. It loses the energy that it has. So it's going to stay attached unless I come along and I get another ATP molecule. So when another ATP molecule comes along and phosphorylates it, it can release. When it releases, it gets energized again. When it gets energized again, it's ready to attach again. It can attach, slide the thin filament, and as long as I have calcium and as long as I have ATP, this process will continue. All right? So the calcium and the ATP will allow the sliding of the filament to continue. That make sense? So, when all of this comes together, this is what I get. It makes sense. Okay? Okay. Okay. Second head.
I don't get the T-tubule part, where that comes from. I thought it was just
the T-tubules invaginate through so that you basically have flow of those ions to the sarcoplasmic reticulum for every single sarcomere. Because you've got to make it, remember, you got to make it move piece to piece to piece. And without those T-tubules invaginating through the fiber, we don't have the ion supply. So basically what I'm seeing, nerve, neurotransmitter, release, ligand, sarcomere, 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 T-tubule, 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 release of calcium, calcium making the troponin and the tropomyosin shift, calcium attaches, myosin head attaches, sliding. And ta-da, you have muscle contraction. Every single time you want a muscle to move, this is the process that is going to be taking place. Is that not pretty cool? Now once again, I'm asking, why I want you learning this at the level I've taught it to you. Because I can guarantee you, a lot of the other professors might not teach you this. Why do I want you to know it at this level? Say that again. It's everything. Not only that, it has the ability to affect every process in your body. Understanding this process, and if you understand what I've taught you at the level of the plasma membrane with the movement of the ions back and forth across that plasma membrane, go ask any nursing faculty, not only here.
That's important, so that we kind of wrap it with your For instance, we have basic code today. We give calcium, we give us numbers.